Welcome to BlackBox Alchemists. In adversarial machine learning and generative AI, we take the dark side attacker, making adversarial staker attacks more query efficient, robust, and stealthy under black box constraints. And we also try to challenge OSCP system provided by Light Poker King team. In this topic, we will briefly introduce our team and the topics we selected. Well, as well, I can say our team, BlackBox Alchemists, is a two-member team, Yu and Zehao. And the topics we selected include two parts. The first part is to improve adversarial staker attacks. And the part two is to challenge one-step control purification system, which is defined by Light Poker King. Let's start with part one, improved adversarial stakers. So part one, improved adversarial stakers. But actually, deep learning vision systems like FIT5230 are vulnerable to physical adversarial staker attacks. So the existing RHDE algorithm can optimize stakers placement, but it's still query inefficient because it might spend a lot of time to query protect and sensitive to small variations in position, angle, and physical conditions. So our problem is how to improve RHDE to achieve more query efficient and robust adversarial staker attacks, but keeping them stealthy and effective. Another work is based on this paper, adversarial stakers, a stealthy attack method in the physical world. And based on the code provided by the author, we made some improvements. And we're going to talk it in details later. So in order to implement our attack algorithm, first we need to do some preparations. We need to set up the environment, just prepare the data sites like LFW or Castle whiteface, because what we want to do is to attack these facial images. And except that, we also need to install other dependencies like FIT5230, BFM, and stakers, so that we can add the stakers on the original image to attack them. And shape predictors and FIT9 package. Once we've already installed all dependencies, it may request to restart session. And after click restart session, we can directly jump to the implementation part. First, we need to import some libraries and then do configurations. Well, in this module, the config is a helper for selecting images from a Torch Vision image folder and keeping the original single image workflow intact. It supports us to do attack on single image or several images, even the whole dataset. We can change the mode to select the images in the whole dataset. And the next one is feature. If this utility extracts some facial landmarks with DLive and builds binary maskers for facial regions. It provides some functions to get landmark coordinates, generate a face region mask, and count frontal faces detected in the image. And then mapping 3D. This module estimates 2D facial landmarks, fits a 3D model to recover across 3D face, and uses a depth projection to a staker, so it confirms two facial geometry. And the pipeline is to detect 68 point landmarks in image coordinates and fade 3D mm and return per pixel depth and aligned to the image. Then apply 2D parabola-based horizontal bending and page rotation. Finally, select a local depth window. If I bend direction and wrap sticker. And then we will need to predict these images because we want to label them correctly. And this model generates predictive face images by placing a staker on a background face, checks whether the placement stays within a facial mask, and queries a FIT9 classifier for top key predictions. It supports both 3D aware deformation pipeline and simpler 2D rotate and pistol baseline. And also, if for defenders, they want to train their model, they just can do some changes on this part. But so far, we just use the pre-trained model based on the Castle whiteface dataset. And then rotate. This model provides helpers to convert RGBA image to an OpenCV compatible array with BGRA channel order and rotate that array around its center. We are preserving canvas sites and filling uncovered regions with a white background. The rotated result is returned as a PLL image with RGBA order. And then stake. Well, this model prepares RGBA stakers and alpha blends them onto a background image. For this part, we will do some background removal via graph card and save it as an image. And also we'll do some alpha blend and attribute staker onto background, right? And resize the staker by a scalar factor or render staker on a transparent canvas. And also prepare some tools to clamp a scalar value into a closed interval or return the 8 neighboring grid coordinates around a specified coordinate with step size. And the heuristics DE, it implements a batched differential evolution optimizer with custom hooks for adversarial search. Finally, we will attack. This is a attack function provided by the author. It's a attack single. In this module, it runs a differential evolution-based black box stake attack. It includes several functions, like predict classes to generate or to bait images, score them with a phase classifier, and build an energy vector. And convert energy to recompute energies after switching to target mode. A single predict to get 2D baseline score for many candidates quickly. And attack exercise called back to stop when classification succeeds and placement is valid. A region produce is a local inbreeding operator that proposes neighbors around current placements. An attack, an end-to-end driver that size search space, runs differential evolution, realizes, and returns states. So here, we can say how it works. When we try to attack one image, so here, we can say the mode is single, and we will attack the image with index, with a specified index. If the model can correctly predict the current image, so when the predicted label equals to its true label of the attack state, we can say the label is same. And when we do single attack, just attacks this image, I can say here we add a staker on it. Actually, the original image, it doesn't have this staker. But when we do the RHDE, what we need to do is to add a staker on the spatial image to prototype the model just to reduce its accuracy. But RHDE, we can see the efficiency is pretty low because when we attack only one image, it costs almost 5 minutes. So we need to do structure change just to improve the efficiency. We want to reduce the time cost. Based on the essence of the heuristic differential evolution, it's really hard to improve it. So yeah, we tried a little bit to reduce the time cost, like load empty scene at once to perform attack on several images. So here we add some new modules to do other modified attack algorithm and try to compare with the original model. So here we do batch attack. Similarly, we only attack the image when the model can correctly predict the image and gives this incorrect prediction. Because the attack will spend a lot of time, so here we only select 3 images to do batch attack. Lastly, we define the analyze function. Finally, we compare the attack single versus a batch attack. We can get a result like this. So we've already covered the part 1 code. So after we run single and batch attack, we run the single attack provided by the author and batch attack defined by adversarials. We log the time, carry counts, and plot side-by-side metrics we can see. Compared with original single attack, our runtime from almost 5 minutes dropped to 43 seconds. And mean queries from 31 to almost 4 times. As for the accuracy, in multi-image runs, the model's accuracy before attack, it reaches to 66.7%. And when we do attack, the accuracy reduces to 0. So this is all for part 1. And then part 2. In part 2, we will challenge the OSCP system, the one-step purification system provided by Team Light Publishing. OSCP is a pre-processing defense. It adds adaptive noise, encodes, purifies features, and decodes a cleaned image. Training combines reconstruction, classification, and perception losses. So this is OSCP, and then we'll see how it works and to perform our attack. All right, this is part 2. In part 2, we will challenge OSCP system from group like Poker King. And its model consists 3 main parts: encoder, purifier, and decoder. And we're going to say it in the following code. First, we need to set up the environment, install necessary dependencies, and then import some related libraries, and define one-step control purification system with adaptive noise, encoder, a purification network, a decoder to reconstruct the image, and add some noise, and do the forward and construct this OSCP system. Then define OSCP training, loads the data site, do a quick training. So far, we already have a complete OSCP system. And then loads the OSCP challenge evaluation system. It has 3 parts: speed challenge, quality challenge, and robustness challenge. Finally, generate a report. So far, we already have OSCP system and its grading system. And then we will implement our attack. Similarly, we will also use differential evolution and staker to do so. Previously, we tried only use differential with staker to attack the mate, but it doesn't work so well because we got only 37.5 attack success rate and a novice attacker grade. The result, well, it doesn't mean it's not a good algorithm. It reveals this is not due to a robust defense or a poor DE search, but a critical logical flow in the text PGD step. So we did some changes, just do some small propagation attacks. So here's our code. First, overlay staker tensor GPU. It returns a new image tensor and show positions on images, and overlay rectangles for placements, and display the original and adversarial images for comparison. And then the important part, generate staker based on differential evolution and PGD attack. So against the purifier, the OSCP system. And it will return the attacked images and placements. Finally, we can see the result of the attack. At the top, there's the original images are predicted by the OSCP system. And then at the bottom is adversarial samples after attacking. Finally, we will use the challenge system to evaluate our attack's performance. As I've mentioned, the challenges include 3 parts: speed, quality, and robustness. For the speed, we got 0. For quality and robustness challenge, we got 4 max. So in total, we received 66.7 of the 100. So this is a code for part 2. Thanks for watching. If you have further questions, feel free to contact us via email.